Open die forging is a metalworking process where a heated steel billet is shaped between flat or contoured dies that do not completely enclose the material. In this project, the steel block used for the exhibit began as a large ingot, which was heated to forging temperature, typically between 1,100 degrees Celsius and 1,250 degrees Celsius. Using a powerful hydraulic press or hammer, the material was repeatedly compressed and shaped into the desired dimensions of 1,000 by 1,000 by 1,200 millimeters. This process refines the grain structure, improves the material's mechanical properties, and eliminates internal voids. Open die forging is particularly suited for producing large, heavy components with high strength and durability, making it the ideal method for preparing the raw block used in the AHMSA fuel cutting demonstration. The steel block surface was cleaned of scale and contaminants, and precise markings were applied to define cut areas, ensuring accurate positioning and optimal cutting performance. To initiate the borehole, an oxygen lance was used to penetrate the solid steel block. This process involved directing a high-pressure stream of pure oxygen through a steel tube, which ignited the metal upon contact. The intense exothermic reaction rapidly melted and oxidized the steel, allowing the lance to cut through the material and create a pilot hole that served as the starting point for the full borehole cutting. After piercing the initial hole, the full borehole was cut using the oxy-fuel cutting process. A specialized cutting torch delivered a precise mixture of fuel gas and pure oxygen to generate a high-temperature flame, which heated the steel to its ignition point. Once the steel began to melt, a focused jet of oxygen oxidized and blew away the molten material, allowing for a clean, controlled cut. The result was a cylindrical borehole 500 millimeters in diameter and 1,200 millimeters deep, showcasing the precision of thermal cutting. The outer contour of the steel block was cut using a large-scale oxy-fuel cutting system, capable of handling the full 1,200 millimeters thickness. The process began by preheating the cutting path with a high-temperature flame, followed by a stream of pure oxygen to initiate and sustain the cut. The torch was guided along the marked outline to produce a precise 1,000 by 1,000 millimeter shape. This required careful control of cutting speed, oxygen flow, and torch angle to ensure straight edges and minimal thermal distortion throughout the thick material. Cutting the cone-shaped cavity presented a particular challenge due to its geometry and depth of 600 millimeters. The process required precise coordination between torch movement, angle adjustment, and flame control. The cone was gradually formed by tilting the oxy-fuel torch at a consistent angle while descending into the steel block. As with previous cuts, the steel was first heated to ignition temperature using a high-temperature flame. Then, a focused stream of oxygen oxidized and removed the molten material layer by layer. Special attention was paid to maintaining a smooth taper and even surface throughout the cut. This stage demonstrated the capability of oxy-fuel technology to perform not only straight cuts, but also complex geometrical shapes in thick steel sections with high precision. Samples were extracted and tested for toughness and strength through Charpy impact tests and tensile tests, ensuring the material met stringent mechanical property requirements. After the oxy-fuel cutting process, the outer contour of the steel block underwent precision milling to achieve the final dimensional accuracy and surface quality. This step involved the use of a large CNC milling machine equipped with high-strength cutting tools capable of handling the hardened steel. The block was securely clamped onto the machine bed, and multiple passes were made to remove any remaining surface irregularities left by the thermal cutting. The milling process refined the 1000 by 1000 millimeters profile and ensured precise right angles and smooth surfaces, essential for both visual presentation and technical evaluation. Additionally, the process allowed for tight tolerances to be achieved, demonstrating the combination of heavy thermal cutting and precision machining in modern steel processing. Drop forging is the process of shaping heated steel by striking it with a massive hammer or press. At channel lock, red-hot steel billets are placed into precision dies and struck repeatedly, forcing the metal to flow into the desired plier shape. This creates extremely strong, durable tools with consistent structural integrity. The trim press is a critical step that follows drop forging. After the plier blanks are forged, they often have excess metal, called flash, around the edges. The trim press uses a hardened steel die to shear away this flash with high force and precision. This ensures a clean, accurate outline, preparing the part for further machining like milling and grinding. The punch press is used to create precise holes or indentations in the plier components, such as the pivot hole where the rivet will later be installed. Using a die and punch, the machine applies controlled pressure to pierce the metal cleanly. This step ensures accurate alignment for assembly and is essential for the smooth operation of the finished pliers. Milling precisely machines flat surfaces and grooves, ensuring accurate fit and function of the plier's joint and gripping areas. The heat-treating furnace hardens the steel by heating it to high temperatures, then cooling it to enhance strength and durability. Adding rivets joins the two plier halves at the pivot point, ensuring a secure, smooth-moving joint for precise tool operation. Grinding smooths and shapes the forged plier surfaces using abrasive wheels. It removes imperfections, refines edges, and prepares critical areas, like jaws and handles, for precise fitting, tuning, and final finishing. And more grinding refers to the multiple additional grinding stages that follow initial shaping. These finer grinding passes further refine the tool's contours, especially around the jaws and pivot area, ensuring smooth operation and consistent performance. Skilled operators use specialized grinders to achieve exact tolerances, improve surface finish, and prepare the pliers for hand tuning and final quality checks. Hand filing involves craftsmen using files to manually refine and smooth small areas of the pliers, especially where machines can't reach precisely. This meticulous process ensures clean edges, proper fit, and a polished finish, contributing to the tool's overall quality and performance. Hand tuning ensures perfect jaw alignment and smooth movement, by making fine manual adjustments to each plier before final inspection. Plier handle dipping coats handles in Channellock's signature blue vinyl, providing a comfortable, non-slip grip and iconic appearance. Blanks precisely cut from proprietary, high-strength, wear-resistant steel alloy. Cold formed through a 5-step progressive process. Each socket is shaped at a rate of 1 per second, ensuring consistent structure, tight grain alignment, and exceptional strength without compromising precision. Each socket is precision ground to achieve an exact, perfectly round diameter, ensuring optimal fit, performance, and torque transfer. Sockets are CNC machined to exacting tolerances, ensuring every dimension meets strict engineering standards. This guarantees a precise fit with fasteners, reduces wear, and enhances tool performance under high-stress conditions, meeting the demands of professional technicians worldwide. Heat treated for 90 minutes at over 1,600 degrees Fahrenheit in a controlled atmosphere to maximize hardness, durability, and structural integrity. After heat treatment, each socket is carefully tempered to relieve internal stresses, balancing hardness and toughness. This process enhances overall strength, prevents brittleness, and ensures maximum durability and extended tool life. Sockets undergo a meticulous 21-step nickel-chrome plating process that enhances corrosion resistance, provides a smooth, mirror-like finish, and adds an extra layer of durability for long-lasting performance in demanding environments. Open die forging is a metal shaping process where a heated billet is compressed between flat or contoured dies that do not enclose the workpiece completely. Unlike closed die forging, this method allows the metal to flow freely, refining the grain structure and eliminating internal voids. It produces components with superior mechanical properties, including enhanced strength, toughness, and fatigue resistance, making it ideal for critical parts like shafts subjected to dynamic loads. Sawing involves cutting the forged billet to precise lengths using industrial saws, preparing it for further machining and processing. Quenching and tempering is a 2-step heat treatment process used to enhance the mechanical properties of steel, especially in components like shafts. First, the material is heated to a high temperature, typically between 800 to 900 degrees Celsius, and then rapidly cooled, quenched, in water or oil. This hardens the steel by transforming its microstructure to martensite. However, quenching also makes the steel brittle. To improve toughness and reduce internal stresses, the shaft is then tempered by reheating it to a lower temperature, typically 400 to 700 degrees Celsius, and cooling it slowly. This process achieves an ideal balance of strength, hardness, and ductility, critical for load-bearing applications. In our in-house laboratory, we perform Charpy impact tests to measure a material's toughness and resistance to sudden shocks, and tensile tests to evaluate its strength and ductility. These tests ensure the shaft meets all mechanical and safety requirements. Pre-turning is an initial machining process where excess material is removed from the forged shaft to achieve a near-net shape. This step prepares the workpiece for precision machining by improving dimensional consistency and surface quality. It also helps identify any surface defects early in the process. By reducing the shaft to closer tolerances, pre-turning ensures better stability during subsequent operations like milling, finish turning, and grinding, leading to improved overall accuracy. Rough and finish milling are sequential machining processes used to shape the shaft with high precision. Rough milling removes large volumes of material quickly to form the basic geometry, while finish milling follows to achieve exact dimensions, tighter tolerances, and a smoother surface finish. These processes are crucial for features such as keyways, slots, and flat surfaces. Accurate milling ensures the shaft fits seamlessly into its intended mechanical assembly. Finish turning and grinding are precision machining processes that bring the shaft to its final dimensions and surface quality. Finish turning removes minimal material to refine shape and concentricity, while grinding ensures a high-quality surface finish and tight tolerances. This is especially important for rotating components, where surface smoothness and dimensional accuracy are critical for performance, durability, and reduced wear. Drilling is a precise machining process used to create holes in the shaft for functional or assembly purposes, such as mounting points, oil channels, or weight reduction. Specialized drilling machines and tools are employed to ensure accurate depth, diameter, and alignment. Depending on design requirements, the process may involve deep hole drilling, counterboring, or reaming for enhanced precision. Maintaining tight tolerances during drilling is essential to ensure the shaft's structural integrity and its compatibility with other components in the final assembly. Non-destructive testing, NDT, is a critical quality control step to ensure the shaft is free from internal or surface defects without altering its structure. Ultrasonic testing, UT, uses high-frequency sound waves to detect internal flaws, such as cracks, voids, or inclusions, by analyzing the wave reflections. Magnetic particle inspection, MPI, is used to detect surface and near-surface defects in ferromagnetic materials. The shaft is magnetized and iron particles are applied. Any irregularities will cause particles to cluster, revealing cracks or discontinuities. These NDT methods provide a reliable assessment of material integrity, ensuring the shaft's safety and performance in demanding applications. Packaging involves securely wrapping and cushioning the shaft to protect it from damage, corrosion, or contamination during storage and transport. Altos Hornos de Mexico, AHMSA, is one of the leading steel manufacturers in Mexico, known for producing high-quality flat steel products for a wide range of industrial applications. With decades of experience and state-of-the-art manufacturing capabilities, AHMSA delivers products that meet the rigorous standards of global industries, including automotive, construction, packaging, and appliances. One of AHMSA's core products includes master coils, which are available in various finishes and coatings to suit different performance requirements. These coils are produced with precise specifications to ensure consistency, durability, and excellent mechanical properties. AHMSA master coils have a maximum outer diameter of 58 inches, making them suitable for high-volume processing and efficient transportation. The inner diameter of these coils ranges between 16 inches minimum and 20 inches maximum, providing flexibility for different slitting and uncoiling systems. With a maximum coil weight of 10 tons, these coils are ideal for industrial-scale production, ensuring fewer interruptions in automated manufacturing lines. AHMSA offers coils in various materials, including tinplate, chrome-coated steel, galvanized steel, galvanneal, galvalume, and cold-rolled sheet. These materials offer different corrosion resistance, surface finish, and formability properties, making them suitable for specific applications such as food packaging, roofing, automotive body panels, and household appliances. The maximum coil width is 54 inches, and the strip width can vary from as narrow as 0.5 inches up to 54 inches, depending on the customer's processing needs. This versatility allows clients to use the steel for a wide variety of fabricated products. In terms of thickness, AHMSA coils are available with a minimum thickness of 0.006 inches and a maximum of 0.0747 inches, allowing for both lightweight and structurally stronger applications. Additionally, AHMSA maintains tight production standards, offering a thickness tolerance of plus or minus 0.005 inches, which ensures consistent product performance and easier downstream processing.